Thank you for your interest in helping the National Weather Service in Louisville by joining the ranks of our Skywarn storm spotters. This training consists of 4 required modules. A short quiz will be administered after each module. Once you've completed all of the modules, you will be able to register in the National Weather Service Louisville Spotter database and will receive a certificate of completion. This module will provide you with information about how the weather works, a brief look at how and why thunderstorms develop. Other modules include the basics of weather warnings, describing the criteria for each type of severe weather warning the National Weather Service issues. Storm spotting, a guide to what cloud features to look for that indicate potential severe weather. And last but not least, information exchange, where we'll discuss how you can get information you need to keep yourself and your loved ones safe, and how you can help others by relaying your observations to the National Weather Service. Additional supplemental modules will be made available in the future, and you are encouraged to take as many of those as you'd like. How the weather works, or a very short course of basic meteorology. The first thing to keep in mind about meteorology and weather is that, with the exception of energy left over at the time of creation of the planet, the sun is the source of all of the Earth's energy. The sunlight it provides keeps us warm and helps plants to grow. When plants die, they decay and become the oil, gas, and coal upon which modern society relies. However, because the Earth is a rotating sphere 93 million miles away from the Sun, with irregular areas of land and water, it is heated unevenly by our closest star. This uneven heating creates hot and cold spots on the planet, and wet and dry ones as well. Nature does not like this unequal distribution of temperature and moisture. It would prefer that everything were equal across the planet. In an attempt to equalize the energy distribution on the planet, Mother Nature moves different air masses around, pushing the warm air toward cold air, the cold air toward warm air, wet into dry, etc. This movement of different air masses around the planet is the basis of what we call weather. Let's take a look at a few more meteorological basics. First, you may remember from grade school science that hot air rises. However, hot air only rises until it reaches air that is warmer than itself. And as air rises, it cools and expands. Next, you need moisture for clouds. In fact, cloud particles are just liquid or frozen water. Finally, you need clouds for precipitation. Rain and snow are just cloud particles that grow too heavy to stay in the cloud, so gravity pulls them down to Earth. Now let's take a look at the ingredients that you need for thunderstorm development. First on this list is moisture, also known as humidity. To see where we get our moisture for thunderstorms in the Ohio Valley, let's first look at a map of the United States. The red circle shows the area where the National Weather Service office in Louisville is responsible for forecasts and warnings. When we look at this map, we see several large bodies of water that could be possible moisture sources for us, including the Great Lakes to our north. The Great Lakes are pretty cold, though, which limits the amount of moisture that evaporates into the air above them, so we really don't see too much moisture from them this far south. This leaves 3 huge sources of moisture that surround our continent, the Pacific and Atlantic Oceans and the Gulf of Mexico. Moisture that comes off the Pacific Oceans enters into the western U.S. However, the Rocky Mountains are a large hurdle for that moisture to overcome going east, and most of it falls out as precipitation on the west side of the Continental Divide. On the other side of the country, air that blows in off the Atlantic brings moisture into the eastern U.S. But the Appalachians serve as a similar barrier for this moisture pushing westward. To our south, air that picks up moisture from the Gulf of Mexico and flows north through the Mississippi Valley sees no obstacles along the way. In fact, the low flat terrain of the Mississippi River Delta is perfect for streaming high humidity northward in the lowest layers of the atmosphere. The Gulf, then, is the primary source of moisture for our thunderstorms in the Ohio Valley, as well as most of the central United States. The second thing needed for thunderstorms is instability. When an object is unstable, even a small force applied to it will cause a large reaction. Let's use this book on dynamic meteorology to demonstrate this concept. While standing upright on a table, just a small force applied to the top of the book causes it to continue in the same direction applied by the force, and it falls to the tabletop. The book is unstable in this position. However, when the book is lying on the table, an upward force applied to it fails to cause it to continue in an upright direction. Instead, as soon as the force is removed, the book returns to its original state, flat on the table. In this position, the book is stable. In the atmosphere, air is unstable when it is warmer than the air around it. This is because warm air weighs less than cold air. That's the reason that hot air balloons rise. While it may seem counterintuitive, In a similar fashion, moist air is actually lighter than dry air. This is because a molecule of water vapor weighs less than a molecule of nitrogen or oxygen gas, which makes up the bulk of our atmosphere. When moisture is added to a given volume of the atmosphere, the lighter molecules of water replace some of the heavier nitrogen or oxygen molecules in that volume, making the volume lighter. Because of this, the most unstable type of air is warm and moist. When warm, moist air lies below a heavier layer of cold, dry air aloft, it is unstable and wants to rise. As it rises, it cools, and the moisture in the air condenses, first forming cloud droplets, and eventually, if enough instability exists, rain, hail, sleet, and snow. The third and final ingredient needed for thunderstorms is a lifting mechanism, or trigger, that causes the unstable air to begin moving upward. The four main forms of lift, or trigger, that generate thunderstorms are, first of all, convective heating. This results from some surfaces heating up faster from daily sunshine than others. For instance, land heats up faster than water, and dark plowed soils heat up faster than lighting soils or pasture land. Second, frontal boundaries between large warm and cold air masses. When cold air moves into a warm air mass, it wedges itself under the lighter, warmer air, forcing it upward. When warm air moves into a cold air mass, because it weighs less, it rides up over the top of the cold air. Third is orographic, or terrain forcing. When air blows toward a hill or a mountain, it can't go through the mountain, so it goes upward, causing clouds and precipitation to form. When the air passes to the other side of the high terrain, most of the precipitation has already fallen out, and the air mass warms and dries as it descends. This is why, with moisture flowing in off the Pacific Ocean, the west slopes of the Rocky Mountains have more rain and snow than the east slopes, which are more arid. In the eastern U.S., the direction of low-level winds into the Appalachians guides which side of this range will see the most rain or snow from a particular storm. The last trigger is convergent winds. These occur after other thunderstorms have already occurred and produce gust fronts. When the outflow of these storms at the Earth's surface collide, the winds, coming from different directions, converge or come together. The air has to go somewhere, and because it's blocked by the ground below it, it's pushed upward. In all of these scenarios, air is forced upward. If the air is unstable, it will continue to rise, then cool, causing the moisture to condense into the cloud droplets of thunderstorms. As with all things in nature, no two thunderstorms are identical. We can, however, classify them into similar categories along a spectrum ranging from the garden variety single-cell storms through various multi-cell complexes to the supercell, which can produce the most violent weather on Earth. Regardless of classification, the key to determining the strength and potential severity of a thunderstorm is the strength of its updraft. A weak updraft results in a non-severe thunderstorm, while a strong updraft can result in large hail and damaging winds. Having just a single updraft, the chance that a single-cell storm will become severe is slight. With additional updrafts, though, the chances for at least one of the many updrafts in a multi-cell complex to become strong increases, so the severe weather threat increases as well. Because by definition a supercell always contains an intense updraft, it's almost always severe, or in other words, there's a high threat of severe weather with all supercells. When all the ingredients for a thunderstorm are in place, an updraft begins. As warm, moist air rises in an updraft, the air cools and moisture in the air condenses to form liquid water, in the form of visible cloud droplets, from the previously invisible water vapor. As the updraft continues, cloud droplets collide to become larger, and in the very cold temperatures miles above ground, liquid water droplets can freeze into ice. When the updraft reaches the point in the atmosphere where temperatures start to warm, known as the tropopause, it begins to flatten out, as it is no longer warmer than the surrounding air. This is why the thunderstorm anvil begins to form. When cloud droplets become large enough that the updraft can no longer keep them up in the air, gravity pulls them down as precipitation, marking the mature stage of the thunderstorm. Eventually, the downdraft overtakes the updraft, leading to the thunderstorm's dissipation. Here's a simple graphic showing the three stages of a single-cell thunderstorm. First, the developing or cumulus stage, where the updraft forms the cloud, but no precipitation is yet occurring. Next, the mature stage, where cloud particles become too heavy for the updrafts to keep aloft. Gravity pulls them earthward, and they in turn pull down air as they fall, creating a downdraft in the precipitation shaft. Finally, in the dissipation stage, the downdraft has completely overtaken the storm and causes it to decay as all of the moisture, in the form of rain and hail, falls to the ground. Seen in the real world, you first see evidence of the updraft as a cumulus cloud forms. After several minutes, the cumulus tower begins to flatten out, indicating the rising air has become cooler than the air surrounding it. As the updraft continues to send warm, moist surface air upward, upper-level winds spread the cloud out into the shape of an anvil, and some of the largest drops, now removed from the updraft, begin to fall as precipitation, creating the downdraft, which will eventually overtake the updraft, causing the thunderstorm to end, and leaving only remnants of the cloud in the sky. Again, this diagram illustrates the entire life cycle of a single-cell thunderstorm from beginning to end. The entire process usually takes just 25 to 40 minutes. Single-cell thunderstorms often develop in areas with little or no upper-level support for their growth and continued development. Seeing the entire depth of a thunderstorm from bottom to top can provide visual clues about the storm's environment and the amount of dynamics available. In this photo, the thunderstorm tower is vertical, indicating weak winds aloft. Because of this, when the updraft begins to flatten out, it forms more of a mushroom-shaped top than an anvil. This is a good indicator that the storm will have a short life cycle, as there is no venting mechanism at the top of the storm, meaning that when gravity starts pulling down the heavier raindrops and hailstones, it will do so directly through the updraft location, choking it off. Unfortunately, due to the abundance of low-level moisture and clouds, it's often difficult to view a storm from top to bottom from the Ohio Valley south of the Gulf Coast. Other than lightning, which is a part of every thunderstorm, the most plausible severe weather associated with a single-cell thunderstorm is damaging winds from microbursts. As mentioned earlier, all thunderstorms have updrafts and downdrafts. But just as not all thunderstorm updrafts are strong enough to produce severe weather, not all downdrafts are either. Those downdrafts that are intense enough to produce damaging winds are called downbursts. Downbursts are further classified by size as either a microburst, with a diameter of less than 2.5 miles, and macrobursts, which are anything larger than that. This sequence of photos shows a microburst, starting with precipitation just beginning to fall in the downdraft below the cloud base. A moment later, as the rain, and possibly hail, has reached the ground, we start to see the evidence of the intense downdraft on the left side of the rain shaft. As the downburst winds spread outward, they meet resistance in the dense air near the surface and are pushed back up toward the sky. In this instance, rain is literally falling upward. As the downburst continues, a second surge of rain undergoes the same redirection as it encounters the rising air of the primary downburst. A few moments later, the microburst winds have spread out horizontally, creating a pattern known as a rain foot. It's under the ball of this imaginary foot that horizontal surface winds reach their peak, which can be as high as 150 miles an hour, the equivalent of an EF3 tornado. For all intents and purposes, multi-cell clusters of thunderstorms are similar to single-cell storms, just in greater numbers. While each individual cell in the cluster behaves much like a single-cell storm, with a lifespan of around 30 minutes or so, the cluster as a whole can go on for several hours as successive storm cells develop along the outflow boundaries created by earlier cells sending out gust fronts during their mature and dissipating stages. Think of a multi-cell cluster as analogous to the whack-a-mole game popular at many amusement parks. As one mole pops into its hole, another rises. Then as that one descends, up pops another one nearby. With more updrafts than an isolated single-cell storm, there is a greater chance of at least one of these storms' updrafts becoming strong enough to support the growth of a large hail and or creating a downdraft strong enough to cause damage as a downburst. For this reason, they pose a higher severe weather threat than single-cell storms. Multi-cell line storms, known as squall lines, are the most common cause of widespread severe weather in central Kentucky and southern Indiana. They are frequently, but not always, accompanied by a striking cloud feature called a shelf cloud, which heralds the onset of the gust front. While ominous-looking, the shelf cloud, which can stretch horizontally to the horizon, does not always precede severe weather, but often is associated with the strongest winds in a storm, both in squall lines and other large storms. Because squall lines usually stretch well beyond the visible horizon, in this case over 700 miles, a radar display provides the best view of the full extent of their coverage. Severe weather doesn't usually occur along the entire length of the squall line. Instead, it's focused in those areas where there are either breaks or bulges in the line. Upper-level winds play a key role in the development of severe thunderstorms. When winds change in direction or speed with height, we call that wind shear. Squall lines typically develop in areas with strong speed shear, but relatively little directional shear. As we saw while looking at single-cell thunderstorms, the updraft of a storm in a low speed shear environment rises nearly vertically. Because of this, when the storm becomes mature and a downdraft develops, it occurs in the same area as the updraft, and effectively overtakes the updraft, causing the storm to dissipate. In a strong speed shear environment, though, when an updraft begins, it becomes tilted by the strong upper-level winds. In this scenario, when the storm's downdraft occurs, it's separated from the updraft. With no downdraft counteracting it, the updraft is then free to continue unabated. The longer it persists, the stronger it becomes, and the greater the chance it will produce severe weather. When thunderstorms develop in an area of strong upper-level winds, there's the possibility that some of these strong winds will make their way to the ground in the downdraft part of the storm. This is especially true with squall lines. Fortunately, there's often a visual clue with the storm when this happens. The shelf cloud is a horizontally oriented cloud that forms on the leading edge of some thunderstorms, especially those in squall lines, along or just ahead of the gust front. Shelf clouds can stretch for miles along the length of a squall line, sometimes from horizon to horizon. The shelf cloud occurs at the intersection of the thunderstorm updraft and downdraft near the base of the thunderstorm, and is an indicator of strong winds heading your way. A similar, though less common cloud, called a roll cloud, may also occur in the vicinity of the gust front along a squall line. Like the shelf cloud, this is an indicator that strong winds are about to occur. The main difference between a shelf cloud and a roll cloud is that the roll cloud is detached from the parent thunderstorm. As the name implies, it may appear to be rolling away from the main thunderstorm, though the direction of the horizontal rotation is actually opposite the direction of its movement. Neither the shelf nor the roll clouds themselves are dangerous. What follows them, however, can be. A good rule of thumb for determining the peak winds associated with the storm producing a shelf cloud is to add 30 miles per hour to the storm's movement. Therefore, whenever a storm moving faster than 30 miles an hour produces a shelf cloud, there's a very good chance the storm will produce damaging winds of around 60 miles an hour. By maintaining good weather situation awareness via the internet, NOAA weather radio, or your local radio or TV meteorologist, you can find out the speed of the storm heading toward you to estimate peak wind speeds whenever you see a shelf or a roll cloud. In some cases, an open channel develops from the very strong upper-level winds down to the ground, allowing the winds to blow for several minutes at a given location and continuing on for several hours with the parent squall line as it races across the countryside. This type of situation is called a derecho, and when it occurs, damaging winds can exceed 100 miles an hour in a path more than 250 miles long. The derecho shown here developed over Illinois and Indiana during the afternoon of July 13, 2004, then plummeted southward into the southern Indiana and central Kentucky areas, producing widespread winds of 70 to 80 miles an hour. This video documents a derecho in a rural location. We first see the shelf cloud and precipitation area approaching from left to right. After the shelf cloud passes over, the observer records hurricane-force winds blowing for several minutes. Note that the direction of the winds indicates the observer turned his camera around and is viewing the storm facing a different direction, as derecho winds always travel in the same direction as the movement of the storm.
Oh my goodness! Oh my goodness! Oh my goodness gracious, we're getting hit with probably 60 to 80 mile an hour winds here. Taking it, man. We are taking it. Wow! Hurricane force. Hurricane force winds.
While shelf clouds can occur with any thunderstorm, they are most common with squall lines. Because of their foreboding appearance, many people mistake them for wall clouds, a feature associated with supercells, which often precede tornadoes. However, there are several differences between the two clouds. While wall clouds occur on the backside of a supercell thunderstorm, shelf clouds always occur on the leading edge of thunderstorms. Shelf clouds are also much larger than wall clouds, often stretching for tens of miles and sometimes extending onto the horizon. Shelf clouds often have ragged and turbulent-looking undersides and may produce what appear to be funnel clouds. However, these are not funnel clouds. These ragged cloud bases occur because of the interface between the thunderstorm downdraft and the air being pushed upward ahead of the storm as the gust front approaches. This intersection does create rotation, but it's in a horizontal plane, not a vertical one. While it's true that squall lines can produce tornadoes, it is not from a horizontal rotating shelf cloud or roll cloud changing orientation and becoming vertical. Not all squall lines produce severe weather, but when they do, it typically happens when a part of the line starts to race out ahead of the rest of it, creating a bulge, also known as a bow echo, for its resemblance to an archer's bow. When this happens, the most likely area for damaging downburst or straight line winds is on the leading edge of the fastest moving part of the line. Sometimes the forward motion of these bulging segments reaches speeds of 45 to 60 miles an hour. Keeping in line with the 30-mile-an-hour rule of thumb mentioned earlier, this can lead to hurricane-force winds of 75 to 90 miles an hour over a several-mile-wide path. As the bowing part of the line continues to surge forward, the threat for damaging winds continues along its leading edge. However, a second location also sees an increased threat for severe weather in the form of tornadoes. Because of the rapid forward motion of the bowing segment, a wraparound area on the northern edge of the bow induces a cyclonically rotating storm segment. Though smaller in area than the broad straight-line wind area on the leading edge of the bowing segment, when the enhanced dynamics associated with this rotation produce a tornado, the maximum wind speeds with the twister tend to be 20 to 30 miles an hour greater than the peak winds associated with the front of the bow. This radar loop from April 24, 2010 is a perfect example of the sequence just described. At the start of the loop, the leading edge of the squall line has already broken off and raced ahead of trailing storm segments. As the wraparound area between the two line segments advances eastward, a tornado develops. The reflectivity scan of the radar captures this event very well. The tornado occurs in a nearly closed donut hole-shaped area of moderate rain, colored yellow, as it passes over central Mercer County. A spotter just happened to be in the right place at the right time on this day and was able to capture most of the 2-minute lifespan of this EF1 tornado. This video highlights several of the difficulties associated with spotting tornadoes in this part of the country. First of all, poor visibility and contrast caused by rain falling on all sides of the tornado. Also, obstructing terrain features like hills and trees. And finally, obstructions from homes and other man-made structures. It should be noted that on many occasions, like this one in 2008, squall lines can be preceded by supercells, with both producing tornadoes. This event, known as the Super Tuesday tornado outbreak because it coincided with the presidential primary elections in several states, produced the second most number of tornadoes in a single day in Kentucky, 26. It's surpassed only by the April 3, 1974 super tornado outbreak, when 28 tornadoes struck the Commonwealth. There were 7 fatalities in Kentucky on this night, 4 in Allen County and 3 in Muhlenberg County. All of the deaths occurred with the supercell tornadoes that occurred ahead of the squall line. The last stop on the thunderstorm spectrum is a storm that is capable of producing the fastest wind speeds on Earth, the supercell. As mentioned earlier, by definition all supercells have an intense updraft, so they pose a high threat for producing severe weather. Not only is the updraft intense, it rotates as well. This rotating updraft is called a mesocyclone and is the precursor to any tornado that the supercell may develop. The supercell updraft, like that of the squall line, is tilted by the environmental winds above the Earth's surface. Similar to the squall line, this results in the downdraft and precipitation area developing away from the updraft region, allowing it to continue unabated for several hours. The updraft of some supercells can become so strong that they literally push clouds into the warmer temperatures of the stratosphere, forming what's known as an overshooting top that bubbles above the anvil where most thunderstorms flatten out. This overshooting top is a great visual clue as to which storms are strongest. Unfortunately, in the southeast United States, the abundance of humidity results in so many lower-level clouds that rarely can spot or see the anvil of storms to look for this telltale severe weather signature. Just as with squall lines, wind shear plays a large role in the development of supercell thunderstorms. Unlike squall lines, though, which rely mainly on speed shear, supercells form in areas that have both speed and directional wind shear with height. The combination of speed and directional shear components helps create a horizontally rotating layer in the atmosphere that, when tilted upright by rising unstable air, becomes vertically oriented rotation, or at least nearly vertical, since the tilted updraft is actually important to the longevity of the storm. Part of this now quasi-vertically tilted column rotates cyclonically, meeting in the same frame of reference as the Earth, which is counterclockwise when viewed from above in the northern hemisphere. All low-pressure systems are cyclones. The other part of the nearly vertically tilted column rotates the opposite, or anticyclonically. All high-pressure systems are anticyclones. Because air rises in low pressure, the cyclonically rotating column reinforces the upward motion of the unstable air, and it continues, becoming the mesocyclone of the supercell. Meanwhile, air in the center of the high pressure descends, which weakens the rising motion of the unstable air, weakening this part of the column. The end result is a thunderstorm developing with a rotating updraft, or mesocyclone. In other words, a supercell. The actual airflow in and around a supercell is a little more complicated than what was just described, as shown in this diagram. However, the description does cover the main processes involved in the development of the supercell's updraft. As with all things in nature, no two supercells are exactly alike, but the basic structure is essentially the same. This image depicts the classic supercell and shows what it would look like on radar. The supercell is easily recognized on radar by its unique shape, called a hook echo. Variations on the classic supercell are the heavy precipitation supercell and the low precipitation supercell, which, as their names imply, either have more or less precipitation than the classic supercell, respectively, and would have a somewhat different appearance when seen in nature and on radar. In the Ohio Valley, classic supercells are most common, but heavy precip supercells increase in percentage the closer one gets to the Gulf of Mexico, due to its abundance of warm, humid air. The updraft of this supercell is shown highlighted in yellow on both the storm diagram and the radar image. Keep in mind that the updraft is rotating. It is this rotating updraft, the mesocyclone, that produces the hook shape of the supercell on radar. The downdraft is depicted by the area surrounded in blue on both the diagram and on the radar image. The downdraft area is associated with precipitation, rain and hail. In this example, the movement of the storm would be moving to the northeast, in the direction to which the precipitation area is spread out. At the bottom of the updraft, commonly referred to as the rain-free base of the thunderstorm, is where one of the most important visible cloud features of a supercell, if present, is located. The wall cloud is a lowering of the rain-free base on the backside of the supercell that often, though not always, precedes the occurrence of a tornado. When seen, this important cloud feature should be watched very closely for rotation. A rotating wall cloud tells you that the intensely rotating updraft of the storm, the mesocyclone, is very active and is trying to extend its way down to the ground. When viewing a wall cloud, one should always look to the ground below the cloud for first evidence that a tornado, the violently rotating column of air, is on the ground. Swirling debris on the ground can occur before a visible funnel is seen. It's important to know that not all wall clouds produce tornadoes, and not all tornadoes come from wall clouds. However, when a rotating wall cloud is seen, it is a very good sign that a tornado could occur at any time. Wall clouds come in all shapes and sizes. Some may show obvious visible rotation or rapid upward motion of cloud fragments, while others look more benign. There are commonalities, though, that distinguish wall clouds from shelf clouds, which we discussed earlier. First of all, wall clouds occur on the backside of thunderstorms under the updraft area. Shelf clouds occur on the leading edge of thunderstorms ahead of the precipitation. Secondly, wall clouds are relatively small, usually a half mile to about 5 miles in diameter, while shelf clouds can stretch for many miles from horizon to horizon. Remember that not all wall clouds produce tornadoes, and not all tornadoes are preceded by wall clouds. but when a rotating wall cloud is seen, it is a very good sign that a tornado could occur at any time. Watch for persistent and sustained rotation, and be prepared to take cover immediately if a funnel descends from a wall cloud or if debris is seen at the surface below one. Congratulations, you've just completed Basic Skywarn Module number 2, How the Weather Works. Let's look over a summary of some of the information in this module. First of all, weather is nature's way of redistributing energy received from the sun more evenly across the planet. There are 3 ingredients for thunderstorms: moisture, instability, and a triggering mechanism to induce lift. The primary source for thunderstorm moisture in our area is the Gulf of Mexico. Warm, moist air is unstable, and when pushed upward, it will continue to rise. Common triggers for thunderstorms are convective heating, frontal boundaries, terrain forcing, and gust fronts. Strong updrafts are needed for severe thunderstorms, and wind shear plays a role in the type and strength of thunderstorms. Severe weather in central Kentucky and southern Indiana is most often associated with squall lines. In recent years, squall line tornadoes are about 3 times more common than supercell tornadoes. Squall line tornadoes tend to be weaker than supercell tornadoes, but are more difficult to see on radar and often have less lead time. The faster a squall line moves, the more likely it will produce severe weather. And severe weather occurs near breaks and bulges in the squall lines. Supercells are the most powerful type of thunderstorm on Earth. Wall clouds frequently occur before many supercell tornadoes. Wall clouds occur on the back side of thunderstorms, and shelf clouds occur on the leading edge of thunderstorms. Once again, you have completed Module 2, How the Weather Works. Please proceed to a brief quiz on this module at the link provided before continuing on to Module 3.